So we're going to take a closer look at the remainder estimation term and how it relates to MVT, or mean value theorem. And so if we take a look at the remainder estimation term, Rn of x, Rn of x is based on the n plus 1 term. So if we're going to truncate the Taylor polynomial at n, we're going to look at the n plus 1 term, and we can get the error estimation term by the Lagrange form of the error term by the derivative of that n plus 1 term divided by n plus 1 factorial. And there's some point b that we can't necessarily find, but we know it exists. And we know it exists somewhere between the center c and the point x that we're estimating. And that term will calculate the exact remainder. Now again, we can't actually find b necessarily, so we're gonna end up using this to bound our error, because we know that b is bounded between some point c, which is our center, and the point x that we're estimating. So we're going to start with the mean value theorem then, and what the mean value theorem states is that the average slope, so if we take a look at the average slope here, which I'll highlight, this average slope here from C to A, that average slope exists somewhere as an instantaneous slope at some unknown point B. And we know that although we can't necessarily find that point B, we know that that point B here exists somewhere between the center and A, the point that we're approximating. So that's the mean value theorem. So we're going to try to relate this mean value theorem to the Taylor polynomial expansion. And to do that, we're first going to frame this slightly differently. And we're going to frame this point C as the center point, the point that we're starting at with our Taylor polynomial expansion. And A, that then represents the point that we are estimating using our Taylor polynomial. So in this case here, if we rearrange then our mean value theorem, so we're starting with our slope, okay, this is our average slope, f of a minus f of c over a minus c, and the other term over here, f prime b, this represents the instantaneous slope at some point b, and we know that they are equal, and we know that b does exist somewhere between c and a. So we take that expression and we're going to multiply both sides by a minus c. So we're going to get rid of the denominator, and we end up with this next expression here. And from here, we're going to just rewrite the f prime b and just write it as f prime b over 1 factorial. And the reason we do that is so that it starts looking more like our Taylor expansion. F of a is a point that we're estimating. F of c is the center, the starting point of our Taylor polynomial. So the first approximation, f of c. So then if we rearrange this and move that f of c to the other side of the equation over here, we're going to end up with f of c, which is our first approximation, plus f prime b over 1 factorial times a minus c to the power 1. And this is going to be equal to the actual value at a. So if we look at this expression then if the f of c represents our first approximation, and if we stop there, the remainder term is going to be what I've boxed here in blue, f prime b over 1 factorial times a minus c to the power 1. That actually represents the remainder term of a zero of our first approximation, and this is just a rearrangement of our mean value theorem. And again, we know that although we can't necessarily calculate b, we know that it exists somewhere between a and c, and that will get us directly to f of a. So if you can imagine what's happening here, we have our first approximation. I'm going to do this in a different color here, blue. We have our first approximation, and then we're going to use this slope to get from a to the exact value, we're going to go from the center C to the exact value that we're estimating at A. So this is kind of the first step in how mean value theorem starts looking like the Taylor polynomial expansion and how this relates to the remainder term.